For regression, regression is still in regression. We assess relationship between in simple regression, relationship between two variables. But here we talk about causal relationship. Causal relationship means one variable cause another on another, one variable effect on another variable, right? So there is cause and effect. When we say A influence on B, it means only A can influence on B, not B on A. Right? So the relationship or the relationship between these two variables is a causal relationship. It's different with correlation. For example, we say, here we say loyalty has a significant effect or positive effect on revisit intention, right? So when we say this one means loyalty caused by revisit intention, and revisit intention influence on loyalty, for example, or vice versa. So in causal relationship, in regression, we have causal relationship. So this is the main difference between regression and correlation. Actually, in regression, one variable, independent variable, predict dependent variable. When we say IV effect on IV influence on DV, also we can say IV predict dependent variable. So IVs are predictor of dependent variable in regression, right? What's actually the meaning of regression? This figure explain the meaning of regression equation. When we say X effect on Y or X predict Y, means part of variance of Y is created by X. Right? So based on this figure, we have two parts, X and Y, and we have some blue dots, right? Blue dots are our sample, our data, our case. For example, for this sample, for this case, X of this sample is this one. Here is X I, for example, right? And for this one, the value of Y is here is Y I, for example, right? So for each case, we have one X and one Y. For example, for respondent number 10, in your data set, you have one value for community attachment. And also you have one value for support for tourism development, right? So let's assume that this is case number 10. And this is the value of support for tourism development. And this is the value of community attachment. Community attachment is our X. So this axis is X axis. X is community attachment here. So for each case, we have one value for IV and one value for DV. This one is another case. This value, this one is another case, and this is value, X value of this case. This is community attachment value for this case. For example, community attachment for this case is 4.2. 4.2, right? And for this case, we have support. So support for this case is support for this case is, for example, 4.3, right? So community attachment for this case is 4.2 and support for this case is 4.3. So each case has one value for independent variable and one value for dependent variable. Okay. For example, if here we have different cases and we put different blue dots in this figure, right? The meaning of regression is the best line that can describe this relationship. The best line that can describe this relationship. So for these different dots, this is the best line that can explain. What's the meaning of best line? Best line means okay. Best line means a line with the minimum difference with real value of y. What does it mean again? Okay. For example, for this data point, right? For this data point, for this data point, here we have xi. So the value of x is xi. Let's say 2.2, right? The value of y is yi. For example, this one is 4.2, 4.1, right? So this is the real value of y. But when we draw this line, based on this line, for this x, the value of y will be this one. So the value of y is different with real value of y. For example, here the value of y is 3.5. So there is a difference between the real value of y, the real value of support for tourism development, and the value from this line, This line, beta 0 plus beta 1 xi, this part. This part represents this line. So I call this part y hat. So y hat is beta 0 plus beta 1 x. This is the best writing I can do based on these tools here. So it's not okay. So y hat is beta 0 plus beta 1 x, this term. But we have one error here. This error is this difference between real y and y from this line, this one. This is one y from this line, y hat. So there is a difference between y hat and real y. This difference, y I minus y hat, is error. Right? So this is the error term for regression equation. So when we want to describe relationship between some IV and DV, DV, for example, y, when we have more than one variable. This is for simple regression, that we have one IV and one DV. If we have more than one IV, so here will be y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus error. So we have error term in undependent variable. So this line can represent this relationship, but with a bit error. Here we have error, right? Okay. So when we have regression represents regression equation or regression line represent relationship between x and y. Here okay. Here you can see y hat is beta 0 plus beta 1 x. Beta 0 plus beta 1 x. So this is equation of this line. Equation of this line. So regression is represented by a line equation, right? And this beta 1 is slope of this line. Slope of this line. So this beta 1, say if x, for example, increase 1 unit, how y will change? For example, if this beta 1 is 0.3, right? Beta. X increase 1, y will increase 0.3. If x increase 2, y increase 0.6. So this beta 1 is a slope of this line and show the relationship between x and y. right? So if x increase 1, for example, here is 1, for example. If increase 1, this is the value that y will increase. Y will increase 3.3. This is the meaning of regression line or regression equation. But we have also this error. This error is not part of this line. This error is for regression equation. Line only is this part. Line only is this part. But this error is difference between real value of y and y from this line. Real value and y from this line, this one. This represents this error. So this is the concept of, this is a mathematical and a statistical concept of regression, right? But what we do in our research, only we calculate this beta and see this beta is significant or not. If this beta is significant, it means x has significant effect on y. The beta, the higher, the better. When beta is higher means the effect of x on y is greater. When beta is very small means the effect of x on y is very small. So based on regression, simple regression or multiple regression, actually we calculate this beta. And based on this beta, we can understand the effect of this x on y is significant and a strong effect or non-significant or weak effect. Right? Okay, so for interpretation of regression, we need to look at this beta, the coefficient of x. So we call this beta coefficient. This coefficient called beta coefficient for regression analysis or regression equation. We have another important criterion to interpret regression analysis. It's R-square. R-square or coefficient of determination. R-square is very common. What's R-square? R-square is explained variance from independent variable divided to total variance of y dependent variable. Here, we calculate variance of y, real y. But some part of this variance come from this x. Some part of this variance come from this x based on this line, regression line. But some part of variance of y come from this error. So we have two parts of variance of y. One come from x and one come from error term. So R-square is ratio of variance come from x, so explained variance by independent variable, and divided to variance from total variance. Variance come from x and variance come from error. So actually, R square is explained variance, and variance come from IV divided to variance come from IV and error, or total variance. So it's the ratio of explained variance from DV to the total variance. This is the concept of R square. So R square, when the R square is high, means error term or variance of error is very low, right? So when R square is high, means numerator is high, and actually the numerator is close to denominator. Here is close to here. Unexplained variance that comes from error is very low. So R square is very close to 1. But if this unexplained variance goes up, so the difference between these two, numerator and denominator, will increase. So the R square will decrease. R square will go down. If this one go up, unexplained variance or variance from error. So we try to get higher R square, but it's not possible always, because actually R square depend on the independent variable and explain variance from independent variable. Sometimes we don't include all independent variables. When we don't include independent variables, all independent variables, this R square will be low. So the value of R square depends on your area of research and previous studies. You need to check what R square got previous studies. If they got high R square, so you expect to get a high R square. But if previous study got just small R square, so you can compare with previous study. And also it depends on type of your research. Sometimes in your research you want to actually examine the effect of some variable on DV, but you are not supposed to include all variables, all predictors of DV. So only you include a few variables. So it means your R square will be low in this case. R square for behavioral science, when you are working in behavioral science, R square 0.2 also can be considered high. But for marketing, based on chain, R square 0.3 threshold. For 0.019 is small and lower. Between 0.19 and 0.36 is, if I'm not mistaken, no, 0.19 and 0.45 is moderate, and is small. 0.45 and 0.67 is moderate, and higher than 0.67 is high. But only is for some study in marketing that you include all variables that influence on DV. But if you include only a few variables, R square can be small, and 0.2 also can be considered high. So for a regression analysis, we need to interpret these two values: beta coefficient and significance of beta coefficient, and R square. What's the hypothesis for regression? As I explained, hypothesis for regression is effect of ID on DV. For example, for this one, yeah, hypothesis is community attachment has positive effect on support for tourism development. So to test this hypothesis, we need to check significance of this beta coefficient. If this beta coefficient is significant, means community attachment has positive and significant effect on Y. Right? Hopefully it's clear and you understand. Two more things for interpretation of regression. For interpretation of regression, also we need to calculate another criterion. This criterion is the multicollinearity variance inflation factor, or VIF. This multicollinearity VIF shows the similarity between two variables. And this multicollinearity VIF should be lower than 5. Should be lower than 5 to be acceptable. So lower than 5 means the similarity of these two variables are not very high. Actually, the similarity between IV and DV should not be very high. If we use very high similar variable for IV and DV, means their assessment of relationship or effect is not meaningful, especially when we have a few more variables, right? So we need to assess this multicollinearity VIF and should be lower than 5. Also, we have tolerance, but tolerance and VIF is very similar. If you divide the tolerance, if you divide 1 to tolerance, you will get VIF. So it's enough to just interpret one of them. So multicollinearity VIF should be lower than 5. Another things for regression, like other previous analysis technique, is effect size. So to calculate effect size, we need to calculate ratio of R square on 1 minus R square. For example, if R square is 0.2, if R square is 0.2, so effect size or F square will be, okay, here is 0.2, here is 1 minus 0.2, so it's 0.8. So the result is 0.25. Okay. F square, R square is 0.2. Here is 1 minus 0.2. So this one is 0.8. So this one is 0.2 divided to 0.8. So equals to 0.25. Right? So this is F square. So this F square, the threshold for F square is 0.02. Lower than 0.02 is not acceptable. But between 0.02 and 0.15 is small. 0.15 and 0.35 is medium or moderate. And higher than 0.35 is large. So here, 0.25 is, what is it? Is moderate effect size. Is moderate effect size. So for multiple regression also, we can calculate effect size and interpret based on effect size. But normality is a requirement and required assumption for multiple regression. If your data is non-normal, you cannot apply simple or multiple regression unless you use bootstrapping, right? Okay, right, regression. And regression, go to linear regression. Because actually the regression that we apply is the linear regression. We created the regression line, right? Before I showed you, right? Linear regression. Okay, for linear regression, in this box, dependent variable, we need to put our dependent variable. Let's say we want to work on this framework. For this framework, support is dependent variable, and we have 4 independent variables, right? This is dependent variable. So when we go to software, we need to transfer support to this dependent box. And independent box, other other window is independent variable. So we transfer community attachment, economic gain, environmental attitude, and involvement. So we have 4 independent variable and 1 DB, right? Okay. Check to see, need to do something here. Okay. In first one is a statistic. Model fit, you can keep this one, and multicollinearity diagnostics. So you need to click on this one to get the multicollinearity VIF, to check multicollinearity VIF. And also if you click on confidence interval, you can get the confidence interval addition to t-value and p-value. So you can just add these 2 ticks and continue. Plots don't have option here, no need to change. If your variable is not normal, you can use bootstrapping. Actually, you have to use bootstrapping. We don't have non-parametric multiple regression. So if your variable is not, one of your variable or few of your variable are not normal, you have to use bootstrapping. Or you use some non-parametric technique. Some technique like partial least square structural equation modeling or non-parametric technique actually based on regression, because they use bootstrapping. They use bootstrapping, but not here. In SPSS, you don't have any alternative technique. So click on OK. This is result of your multiple regression. 3 tables, but actually 2 are more important. You need to interpret for multiple regression. Okay. First table is model summary. Model summary include adjusted R-square and R-square. So your R-square here is 0.300, but adjusted R-square is 0.293. Adjusted R-square is a bit better than R square. In adjusted R square, software do some modification on R square based on number of variables to get a better value independent from number of predictors. So you can report any of these R square or both. You can report R square and adjusted R square. So the value of R square here is 0.3 and adjusted R square is 0.9. Always R square and adjusted R square are very close, right? So how interpret R square? Based on your field, previous studies, and your research. Here, we actually want to see effect of some variable on support. Community attachment, support, attitude are variable in behavioral discipline. So we investigate behavior of people. And there are many more variables that influence on support, but we didn't include because actually we don't need to include this variable in our research, right? So for behavioral science, the value of 0.3 is actually high. Higher than 0.2 can be considered high in behavioral science. So this is the interpretation of R square. Report R square and interpret based on your field, right? This is one of the very important table. You need to report content of this table. For assignment, you have to transfer this table, but for your paper and your thesis, no need to transfer this paper. Just you need to report R square values. But in your thesis, probably you need to provide all these tables in appendix. Okay. So this is the value of R square and very important to interpret result of multiple regression. Actually, some studies when want to interpret R square, consider R square as a model fit or predictive capability of our framework. It means when R square is high, means your independent variable, you include many related independent variable in your framework. So because of that, your R square is high. Or in other words, your error term is very low. You remember here? Error term here is very low. So it can be considered model fit for multiple regression, but it's not common. The best thing is to call and interpret R square. Okay, so this is the first table and important table and information for interpretation of multiple regression. Another table is ANOVA. This table is not very important. Okay, you can report it or you can skip. This ANOVA table and this F square and significance only show that there is at least one when this is significant, when this p-value is significant, when the result of ANOVA is significant, it means at least there is one significant relationship between IV and DV, at least. But you cannot make sure more than one. And actually you don't know this significant relationship or effect of IV on DV is one or more than one. But this ANOVA can show at least there is one significant relationship between IV and DV. So it's not, you can get this information from this table. So here you don't have informative result. Okay? But the most important table is this table. The most important is this table. Here we can see beta coefficient and significance of beta coefficient. Significance of these beta coefficient. If this beta coefficient is significant, means X has significant effect on Y. Means effect of your hypothesis for effect of X on Y can be supported. So the information comes from this table. Here we have constant value, community attachment, your ID. Community attachment, economic gain, environmental attitude, and involvement. So you have your independent variable and another row is constant. Constant is this value. This value is beta 0, is intercept in this equation. This beta 0 is intercept in this equation. Actually, this is intercept of this line. When X 0, what's the value of Y? So this intercept is this constant value is intercept. Okay, so you have your IV and intercept here. This is beta. So the beta value, beta 0 is 1.5, beta 1 is 0.21, beta 2 is 0.016, beta 3 is 0.167, and beta 4 is 0.226. If we have 4 IV and 1 beta 0, 1 intercept, right? But addition to this beta, we have another beta that is more meaningful and useful and informative compared to this unstandardized beta. So the first one is unstandardized beta. And exactly same as this beta here. Beta 0, beta 1, beta 2, 4, 5. If we have x2, x3, x4. Right? But here we have standardized beta. In standardized beta, actually we standardize our variable. And when we standardize our variable, in this model, this line will cross 0 point. Yeah, will cross. So this line, when we change beta, unstandardized beta to standardized beta, this line will change to something like this. You assume this is live, not here. Okay. So for a standardized beta, we don't have intercept. We don't have beta 0. Only we have beta 1, beta 2, and beta 3. So this is the value of standardized beta calculated based on this line, the line that cross 0 for X and Y. And this is calculated based on standardized value of X and Y, value of independent variable and dependent variable. Okay. So it's better to better to interpret standardized beta. So this column. Okay, a standardized beta is different with unstandardized. Here is 0.216, 0.035, 0.16, 0.295. So this is standardized beta, and most important things for multiple correlation interpretation. Okay, so this is beta for each relationship. First one is for effect of community attachment on support. Second one is for effect of economic gain on support. Third one is for effect of environmental attitude on support. And the last one is for the effect of involvement on support. Dependent variable is support. Right? Here you can see dependent variable. So dependent variable is support, and we have 4 independent variable with beta. Okay. Now, here you have t-value and p-value for these 4 beta. This is p-value 0.91, 0.77 for second one, 3.2, and 6.064. These three t-value is higher than 1.96, right? So for this tree, t-value is higher than 1.96 for this one and this one and this one. And p-value is lower than 0.05 for this tree. For this tree, p-value also is lower than 0.0. And what about confidence interval? Lower level, upper level. Lower level is 0.105, 0.317. For this one, lower level is minus 0.025. And upper level is 0.05. So 0 falls within this range. 0 is between these two values. And also this consistent with this p-value. P-value is higher than 0.05, right? Higher than 0.05. So for second one is not significant based on t-value, p-value, and confidence interval. And for these two, also lower level and upper level are positive. And 0 is not between lower bound and upper bound. So the effect of community attachment on support is significant based on t-value, p-value, and confidence interval. And the value is 0.216. So there is a strong relationship, strong effect of community attachment on support. But there is no significant relationship between community, economic gain, and support. So the effect of economic gain and support is not significant based on t-value, p-value, and confidence interval. So this effect cannot be supported by the result. And these two also are significant based on t-value and p-value and confidence interval. But among these three significant independent variable, which one is more important? Which one is more important to predict Support for tourism development.
Involvement.
Involvement. So based on the size of beta coefficient, we can see what variable, which variable is more important. Here, involvement is the most important, then followed by community attachment and followed by environmental activity. And economic gain is not important variable to predict support. Okay, so this is for interpretation of beta coefficient. So you can explain beta coefficient based on TP and TP and P values and confidence interval. Okay. Another important things is multicollinearity VIF. Okay. Multicollinearity VIF for first variable community attachment is 1.7. For second one is 1.18. For third one is 1.48. And for involvement, last one is 1.35. So for all of these variables, all independent variable, VIF is lower than 5 and acceptable. If one of them is higher than 5, for example, first one is, you can see the first one is 5.7. And another one is involvement is 6.2. If you have value of VIF higher than higher than 5, it means you have huge similarity. You have high similarity between community attachment and involvement. What you need to do, you need to look at the item of each variable and see what's the what items in the community attachment and involvement are similar items. You can delete similar items to decrease the item. Later, when we perform multiple regression, also we can check statistically this similarity. Later, we will discuss cross-loading. And using cross-loading also, we can detect this similarity and see which item in a variable are similar, so we should remove these items to reduce VIF, multicollinearity VIF. Okay? So this is two tables that are worthy to interpret, and you have to interpret. First one is model summary, and the second one is coefficient. For collinearity diagnostic, you have information here, so no need to go to this table. You have information of VIF, and the interpretation of multicollinearity VIF is enough. The values of VIF enough to interpret multicollinearity and should be lower than. Okay. So this is for interpretation and performing multiple regression.